Good afternoon, everyone. Welcome back. I'm Michelle Saner, and today we are going to be talking about limiting reactant and theoretical yield as it pertains to stoichiometry. So as we move forward in the study of stoichiometry, we start to get into the why we do this. Our goal is to be able to predict how much of a product we can create in the lab or in a real life setting, given a set and specific amount of reactants. So we're going to do some calculations today to show how to do that. So our learning target for this afternoon is that by the end of the day, you can determine the limiting reactant and the theoretical yield of a chemical reaction given only a balanced chemical equation and an initial quantity. And you'll need to use your knowledge of the periodic table, of molar mass, of mole ratio, and all of the other stoichiometry terms that we've come across in order to do so. So let's use this thought example that I know I keep coming back to this bicycle. So let's say that we needed a chemical reaction for a bicycle, and we're going to dumb it down to make it really, really simple, that 2 wheels and 1 frame are enough to make 1 bicycle. So this is a recipe or a balanced chemical equation. Given the fact that we have, let's say we have enough in our garage, we have 6 wheels and 4 frames. How many bicycles would we be able to make? So if I have 6 wheels and it takes 2 wheels to make a bicycle, I can intuitively decide that I can make 3 bicycles with those 6 wheels. And with my 4 frames, I can make up to 4 bicycles. Only one of these can I actually make. So the limiting reactant and the theoretical yield are tied into one another. A common misconception is that the limiting reactant is the quantity with a smaller number, but this isn't always the case. In fact, it's not, only half the time is it the case. So we need to look at the overall ratio. For me, for this bicycle, it takes 2 wheels. So 6 wheels, if I started with 6 wheels, I could make up to 3 bikes and no more. I couldn't make any more than 3 bikes. With my 4 frames, I could make 4 bicycles, but I would have run out of wheels. So the only value that I could truly make is the lower amount of products, the 3 bicycles. We call this the theoretical yield. And that theoretical only refers to, it's the amount that we could possibly make in the lab, not accounting for error and things like that. We then say that the reactant that produced the lowest quantity is the limiting reactant. So you can't look at the number or the quantity of a substance that's given and automatically determine what the limiting reactant is. It's not always the smallest value. So let's look at this a little bit more in depth. The limiting reactant is the reactant that's used up first in a chemical reaction. So in our case, it was the bicycles. This is called the limiting reactant. It's not necessarily that it has the smallest starting amount, just like in our bicycle example. 6 was greater than 4, and yet the 6 bicycle wheels were used up first. So if you look at this bicycle example, although we started with the 6 wheels, the ratio of 2 wheels to 1 bicycle meant that the wheels are used up faster and only 3 frames are required, and 3 bicycles were able to be produced. So 1 frame ends up being left over and unused. So because the wheels were used up first, we call this the limiting reactant in this particular product. The theoretical yield, on the other hand, is how much you can make of the product based on the amount of reactants that you can start with. So it is theoretical only because it's in a lab setting and there may be error that results in a different amount, not because your calculation is incorrect. So your theoretical yield is a precise amount that we would expect to make theoretically in the lab. So if we look back at the bicycle example, the theoretical yield when given 6 wheels and 4 frames was 3 bicycles, because after making those 3 bicycles, you couldn't make the 4th because you're out of wheels. So theoretical yield and limiting reactant are completely interconnected to one another. And determining the theoretical yield allows you to determine the limiting reactant. So here's a generic procedure for solving, and I'll walk you through the steps that I took with my bicycle example as our kind of demonstration. So number one, determine what it is that you're given and what it is you're trying to find. Typically, you'll be given amounts of reactants, specific amounts. So in this case, I was given 6 wheels and 4 frames, and I'm trying to find the theoretical yield of bicycles that I could make, the theoretical yield of the product, and the limiting reactant for this product. The second step is to determine your mole ratios of each reactant compared to the product. So that is to say, it will take 2 wheels to make 1 bicycle, and I've written that over here. The other ratio that's important is it will take 1 frame to make 1 bicycle, and I've written that mole ratio over here. Both of these are going to become important in the next step. To convert between the number of moles and the mass, if you're doing a real example, in this example, it's not applicable because we're looking at a mole-to-mole type calculation. So we're ready to perform a stoichiometry calculation for each of the reactants given. So given 6 wheels, I set it over 1. In the next step, I drop wheels down below and use the mole ratio that we calculated in the last step. That says it takes 2 wheels to make 1 bike. Wheels cancel wheels. I'm left in units of bicycle, and my answer is 6 divided by 2, or 3 bicycles. And that's how we got there. If we use a picket fence formula, we already did this in our head earlier, but now I'm showing how it works on a unit analysis. So using the mole ratio of 1 frame to 1 bicycle, I start with 4 frames that I was given, set it over 1, drop the unit of frame down in the next step so that it cancels. 4 times 1 divided by 1 is 4 bicycles. So I have enough frames to make 4 bicycles, and I have enough wheels to make 3 bicycles. So really, I only have enough ingredients to make the smaller amount, the 3 bicycles. So you determine the lowest possible amount of the product, and that is our theoretical yield, 3 bicycles, and you circle it. And then you look back to the reactant that gave you that smallest value. So this corresponds to, I started with the reactant of wheels. So then wheels becomes my limiting reactant, the reactant that produces the smallest amount. Whatever thing you started with that gave you the smallest quantity possible is your limiting reactant. You're limited to make more by that reactant. You could make more if it wasn't for the limited amount of that reactant. So in this case, it is wheels. So let's do the same thing now, but with a real chemical equation. So given this chemical equation, and of course we can get some mole ratios out of here as well, 8 zinc metal reacts with this sulfur to this 8 sulfur complex to form 8 zinc bonded to sulfur. So if 2 moles of the zinc reacts with 1 mole of this S8, so I have 2 moles of this, I have 1 mole of this, how much of this product can I make? What is the limiting reactant? So I've written my given down here, 2 moles of zinc, 1 mole of S8, and I've also identified the mole ratios that I'm going to need. So how much zinc will it take to make this zinc sulfur complex? How much of this sulfur complex will it take to make this zinc sulfur molecule? So it's going to be 8:8 ratio on the first. So I wrote that down here. 8 moles of zinc produce 8 moles of zinc sulfide. And then down below, I look at the implied 1 mole of the S8 that creates 8 moles of ZNS. So I have all of the information I need to go ahead and solve for the moles. So I made a little bit of extra space down here. Starting with the given, setting it over 1. Moles of zinc, and then I drop that unit down into the next step, and I use the mole ratio. That there are 8 moles of zinc will produce 8 moles of zinc sulfur. So I take 2 times 8 divided by 8, and I get 2 ZNS. So I have enough zinc to make 2 moles of this ZN sulfur, the zinc sulfur. Okay, so now let's do the same thing, but with the other reactant. So we take this 1 mole of sulfur, we'll bring it down with us, set it over 1. In the next step, I know I need to put the moles of S8 down below so that they cancel. And I compare, this is again my mole ratio. In this case, I'm comparing the second reactant to see how many products I can get from it. So 1 mole of S8 cancels with 1 mole of S8. I'm left in moles of ZNS. So I multiply through, divide through, and I have enough of this S8 to produce 8 moles of ZNS. So I have enough of the first reactant to produce 2 moles of the product, and I have enough of the second reactant to produce 8. So really, I only have enough of my total ingredients to produce 2 moles of zinc sulfur. So this is my theoretical yield, the smaller value. So I do a multimole problem for every reactant, then I find the smallest amount I'm able to produce, and that is my theoretical yield. Now, looking back at the reactant that gave me that theoretical yield tells me that zinc, 2 moles of zinc, is the limiting reactant. It's the reactant that gets used up when I make that 2 moles of the product. Once I've used up all of the zinc, I have no more zinc to continue the equation. So even though I have excess of this S8, I can't make any more once I've made that 2 moles of zinc sulfur, because I'm limited by the low number of moles of zinc that I can start with. So the theoretical yield is the lowest possible amount of product after you've done the math on all the different reactants. And the limiting reactant is the reactant that's used up first and produces that lower, smaller amount, the theoretical yield. So we'll be doing a little bit more of this in class, but hopefully that gives you a little bit of an overview of how to solve these limiting reactant problems. I hope you're doing well and you're having a great day. And we'll practice more when we see each other in class next time. Bye.